Oh, hey everyone. In this video, my plan is to go through the entire derivation of the heat equation, so talk through where the heat equation comes from, and then actually go through a whole heat equation problem in a single setting. And this is going to take a little bit of while to get through, but as long as we have a pretty basic understanding of something called a Fourier sine series, we should be pretty good to go. So the one thing that we need is I need for you to be able to compute the Fourier sine coefficients. So in particular, if we have a function, let's say some f of x, that we want to express as the sum from n equals 1 to infinity of some coefficients that depend on n, call them b sub n's, times sine of some n pi over L times x, I need you to know that these b sub n's can be written as 2 over L times the integral from 0 to L of our function f of x times sine of n pi over L times x. So as long as we have this down, you should be able to follow through the derivation of the heat equation and the solution to the heat equation. So let's go ahead and let's get started. So the way that I like to visualize the heat equation is something like this. Let's imagine that we have some sort of an insulated rod. And when I say insulated, I mean it's insulated along the length of the rod. And the endpoints are left open, right? So kind of imagine taking a pipe and wrapping it in insulation and just leaving the ends exposed, right? For the problem that we're gonna look at today, and the way that I typically like to introduce the heat equation though, I tend to like to say, let's imagine that both the ends of the rod are held at 0 degrees. And I'll go ahead and I'll kind of talk about the length of the rod also. I'll say, let's let this correspond to a position of x equals 0, and let's say this corresponds to a position of x equals L. We'll just call the length of the rod L, okay? Now, where the heat equation starts to get interesting is we pretend that we're going to start with some initial heat distribution. So meaning that there's, at every point along the length of the rod at some time t equals 0, that we can associate each point along the length of the rod with a temperature. So what I mean by that is that if I were to perhaps come up and graph the temperature on like a imaginary y-axis here, the temperature here might be 0, but as we move a little to the right, we might have a higher temperature, and maybe towards the middle of the rod, our temperature dips down a little bit, curves back up, and then our right endpoint is still held at 0 degrees. So we'll say this graph that I just drew corresponds to some time. Let's say an initial time t equals 0, okay? And if you would like, you can go ahead and you can imagine this being on some sort of a Cartesian plane. So you could almost imagine this as being like an x-axis, and you can imagine this axis here representing the temperature of the rod. So I'm going to use a different variable for temperature than we might expect, but I'm going to just use x to denote along the x-axis. But the temperature, I'm going to use the letter U to denote the temperature. Why the letter U? It seems to be just convention to use the letter U, but we're going to use we're going to use U to denote the temperature throughout the length of the rod. And here's something that we kind of have to notice, right? At t equals 0, the temperature at this point is whatever's up here. I'm not going to even argue scale, but as time changes, the temperature at that point is also going to change. So the temperature is not just going to be a function of position, it's also going to be a function of time. So when I'm talking about the temperature or the y-axis, it's actually going to be some u of x and t. Okay, so as I was kind of hinting at, I was saying that the temperature throughout the length of the rod is going to change as time changes. So let's go ahead and let's kind of imagine if we heated our rod up to this heat distribution, we held both the ends at 0 degrees, and we said, let's wait maybe a minute or a second or just some 1 unit of time. Let's think about what would happen to the temperature throughout the length of the rod. So I'm going to go ahead and I'm going to sketch what happens after maybe 1 second or 1 unit of time. Well, kind of what I'm seeing is if I'm looking at a point like this guy up here, I have a high temperature, and surrounding that high temperature is a bunch of low temperatures. So if I kind of imagine letting time go on a little bit, it makes sense to me that the temperature up here is going to fall. And likewise, the temperature here is also going to fall. It's surrounded by slightly lower temperatures, so the temperature there is going to decrease. And if I'm looking at a point down here, like this relative minimum type point, or this point in the valley, we might expect that the temperature here is going to rise because the temperature a little to the left and a little to the right of that point is higher than the temperature at this point. So here our temperature might go up, just slightly. Okay. There's one other point on the graph that I do think is interesting to consider. Maybe two other points on the graph that are interesting to consider. And those might be something like this point right here and this point right here. Right? If you look at this point here, you might see, hey, our heat distribution almost looks straight at this point. So if I want to know how is the temperature here going to change, well, if I move a little to the left, the temperature might be a little higher, move a little to the right, the temperature is a little lower, but on average, the temperature at that point's not going to change. And the same thing's going to happen over here, right? If I start at that point, move a little to the left, temperature's a little lower, move a little to the right, temperature's a little higher, on average, the temperature at that point shouldn't change. So at those few points, we can expect that our temperature is not going to change. So let's go ahead and let's maybe try to envision what's going to happen as I let time go on for one unit of time. The ends are still going to be held at 0 degrees. The temperature up at our peak is going to drop a little bit. The temperature here is not going to change much. Temperature here is going to rise a little bit. Temperature there, not going to change. Temperature here is going to be a little less, and we're still holding on to 0 degrees at the right endpoint. Right? So that's probably going to show off what happens after 1 unit of time. Let me erase some of these arrows because this is just going to get a little ugly to look at if I keep all of these arrows in here. All right, so now we have a new graph that we're looking at. All right, I'm going to go ahead and erase the red graph for just a second. I will bring it back in a moment. But now that we have this picture here, we can kind of see what's going to happen. Again, temperature here is going to decrease. Temperature here is probably going to stay right about the same, and our temperatures over here are going to begin to decrease again. So if we do go ahead and try to draw what happens perhaps when t equals, let's say 2, well, our ends are still held at 0 degrees, and the temperature throughout the length of the rod is just kind of going to start to decrease throughout its length. And then if we keep this going, so perhaps let's do one more. Let's see what happens when t equals 3. Again, the ends of the rod are going to be held at 0 degrees. And eventually we're going to reach a point like this. And as we keep going, we can kind of see that the temperatures are just going to continue to decrease until we have kind of a steady state solution throughout the length of the rod of a temperature of 0 degrees. So I think this picture here does a pretty good job of showing off how heat will dissipate throughout the length of the rod as we let time go on. All right. So the thing is we haven't really gotten to a point where we're talking about a differential equation yet. We're kind of trying to understand the physical scenario, and from the physical scenario, we want to build up a differential equation. We want to build up some understanding of how we can write something down and try to solve something, okay? So let's go back to describing how that temperature changed, right? And let's look at maybe just one point. If we were looking at some point like this, right? We said the temperature here was going to decrease as time goes on. And we said that if we had some sort of a point like this, we said that as time goes on, the temperature here was going to increase. And we even said something about what would happen in between those 2 points, right? So we said that if we had like a straight line segment, the temperature here isn't going to increase or decrease, right? It's one of those, oh, it might increase over to this side, but it might decrease over to this side. Well, right in the center, the temperature is not going to change at all. So it kind of seems like the way that temperature is going to change is going to be somehow related to the concavity of the graph of the function, right? And in particular, I think it makes sense to say that the rate at which temperature changes is going to be proportional to the concavity of the graph along the x-axis. Let me go ahead and slide this over here. Is proportional to the concavity So now we kind of have like a verbal description of this scenario. And if you're one of my calculus students, you're probably seeing one word here that really, maybe two words, that screams some calculus at you. And those two words are this idea of a rate and this idea of concavity. These are two words that sound like they'd come up in a Calc 1 class, and they're two words that we used all the time when we were studying ordinary differential equations. So let's go ahead and let's see if we can turn this mathematical sentence into a mathematical equation, right? So the first thing we have is a rate. Well, the rate of what? Well, the rate at which the temperature is changing. Well, what denotes the temperature? Well, the temperature is denoted by this u of xt. So a rate sounds like a derivative with respect to time, but since u is a function of both position and time, we'll have to take partial derivatives of u with respect to time. So here's our rate at which the temperature is changing. And that's going to be proportional to, so we'll introduce some sort of a constant of proportionality. I'll call that constant alpha. And I'll make it positive because a couple things to just note, right? If we're concave down, our temperature is going to decrease, and it seems like if we're concave up, our temperature is going to increase. So the rate at which temperature changes is going to have the same sign, if you will, as the concavity. So how would we denote concavity? Well, we know concavity is a second derivative, and it's going to be the second derivative of our temperature distribution with respect to the position, so with respect to x. So now we have kind of an equation representing the scenario. We have an equation that reads the rate at which the temperature changes is proportional to the concavity is proportional to the concavity of the heat distribution throughout the length of the rod, right? And we'll normally see the heat distribution written like this, or sometimes we'll just simply see the heat distribution expressed as u sub t of xt equals alpha squared of, let's say, u sub xx of xt. Either of these represent the heat equation. All right, so that alpha squared value, constant of proportionality, kind of describes the speed at which, or the rate at which heat is dissipated throughout the rod. Sure, we could go into more detail about the alpha squared, but when we start looking at an example of this, we're just going to pretend that alpha is equal to 1. We're going to kind of ignore units, but if we were interested in units, so talking about like degrees Celsius per hour or something, one of these things where we're actually describing like a physical interpretation of a heat problem, that's something that we could do, right? But with the way that this is set up, we're just going to pretend it's equal to 1 and do all of the math kind of in an entirely unitless sense. All right, so let's go ahead and let's maybe set up a heat equation problem that we can solve. So let's say we want to solve the heat equation. And our heat equation is going to look something like u sub t of xt equals uxx of xt. So this is our heat equation with alpha equals 1. Right. Subject to, right? So remember there were a couple conditions that we had to subject our heat equation to. Well, what we have two boundary conditions that say hold the left and the right endpoint at 0 degrees. So if I want to hold the left endpoint at 0 degrees, I would write u of 0t equals 0. And if I want to hold the right endpoint at 0 degrees, I would write u of lt equals 0. So these are what we call boundary conditions. In other words, these describe what happens at both the left and the right endpoints of our rod. Right? And there's one other type of condition that we need to subject our differential equation to. And that's going to be that initial heat distribution. So our initial heat distribution looks something like u of x t. And we can try to solve this in general for some arbitrary function, f of x. I'm going to say probably a bit later on in this problem, we might pretend that we have a function f of x equals, let's say like 2. So basically what this is saying is the temperature throughout the length of the rod is 2 degrees 20 degrees, some just arbitrary value, I guess. And we're still holding the ends at 0 degrees. So basically, as soon as we press the timer, we're going to imagine the temperature throughout the length of the rod decreasing. Right? But we'll try to talk about this in the most arbitrary sense throughout the bulk of the problem, and maybe right towards the very end, we'll actually go through and we'll see what happens if we use f of x equals 2. Right? So, as I mentioned, this is what we call an initial condition. All right, so we've got a nice heat equation stated, we've got boundary conditions stated, we have an initial condition stated, we have all of these conditions stated, and now we need to ask ourselves, how do we solve the heat equation? How do we solve a partial differential equation? And really, you can't jump into this trying to use the same techniques that you used in the ordinary differential equation sense. We can't just look at this and say, oh, well, clearly like an exponential function is going to satisfy this, or clearly a trig function is going to satisfy this. It's a bit trickier than that. So what we do is we actually make one assumption as we go ahead and we begin trying to solve our heat equation. And that assumption goes a little something like this. We want to assume that the solution to the heat equation, right, our function u of xt, is going to look something like a function of x times a function of t. And to me, this seems like a reasonable guess as to what the solution is going to look like, because x and t are these linear, or are these independent variables. Position has no relationship to time, time has no relationship to position. So we should be able to imagine that these are just two independent functions that are going to satisfy the heat equation, okay? Now we can go ahead and we can actually take our derivatives and we can start substituting these back in just like we did with our guesses for ordinary differential equations. So what this gives us then is if we take a partial derivative of this function with respect to time, well, x is being treated like a constant, so capital X is just a constant function in this partial derivative sense. So we'll just take a partial derivative of t with respect to t, but that would be the same thing as just taking an ordinary derivative. Right? And something similar happens if we take two partial derivatives with respect to x. Here, it will take two partial derivatives of x with respect to x, but since x is only a function of x, those will be the same thing as if we were to just take an ordinary derivative, or two ordinary derivatives of x. And then here, t is being treated like a constant, so capital T of t is acting just like a constant. Right? Now we can substitute these back into the heat equation. So what does that look like? Well, remember what our heat equation was. Ignoring the of xt, our heat equation was the partial derivative of u with respect to t equals two partial derivatives of u with respect to x. So we'll substitute these back in, and we'll have x of x times t prime of t equals x double prime of x times t of t. Right. So from here, we're kind of stuck again. There's really not a good place to go from here that helps us get any closer to the solution. So what we want to do is we actually want to use like an extension of a trick that we talked about early on in the semester. So almost one of the first things that we thought about. We want to try to separate our variables. So let's go through this process of separation of variables. Let's get our x's by themselves and let's get our y's by themselves. So we can actually divide both sides of this equation by t of t and x of x, and that leaves us with t prime of t divided by t of t is equal to x double prime of x divided by x of x. So from here, we can go ahead and we can look at this, and if you notice, this has to be true regardless of which x values you plug in and which t values you plug in, right? So x and t are are independent variables. So this has to be true when t equals 0. This has to be true when t is 1. This has to be true when t is 2. This has to be true when t is 3. This has to be true when t is 4. And it has to be true for all values of x then also. So the only way that this can be true is if one of these is equal to a constant. And the only way that one of them could be equal to a constant is if both of them is equal to a constant. So what is that constant? Well, let's just give it a name. Let's use the constant lambda. All right. So from here, what we really have is we have two equations. We have a t prime over t, I'm going to ignore the of t's and the of x's from this point forward, is equal to lambda. Well, if we multiply both sides by t, we end up with t prime equals lambda t, and if we subtract a lambda t from both sides, we have t prime minus lambda t equals 0. That right there is an ordinary first order linear differential equation with constant coefficients. That should be a fairly simple differential equation to solve. And if we look at the second equation that we get, we have an x double prime over x equals lambda. Go ahead and multiply both sides by x, and you have an x double prime equals lambda x. If you subtract lambda x from both sides, you have an x double prime minus lambda x equals 0. Again, now you have a second order linear homogeneous differential equation with constant coefficients. Both of these we know how to solve. And the interesting thing about both of these now is now we have two ordinary differential equations. So we've taken partial differential equations, made one assumption, and we turned that one partial differential equation into two ordinary differential equations, two equations that we do know how to solve. The big issue now is we're trying to simultaneously solve two differential equations that have a value of lambda in common with both of them, right? And the thing is right now we don't know anything at all about that value of lambda. So we'll have to think a little bit harder about that, okay? So before we think too much about lambda, let's think about which one of these differential equations we might want to solve first. I'll be honest, it doesn't really matter which one of these we solved first, but there is one that might be a little helpful, might be a little more helpful or easier to solve first. And that's going to be the second one in x, right? And let me see if I can convince you why that second differential equation in x might be easier to solve. It comes down to looking at the boundary conditions, okay? So let me go ahead and let me restate our boundary conditions. So our boundary conditions said u of 0t is equal to 0 and u of lt is equal to 0. Well, from our assumption, we said that u was going to be a function of x times a function of t. So if I want u of 0t to be equal to 0, well, that means I want x of 0 to be equal to 0 and t of t to be equal to 0. Well, the one thing that I do not want is I do not want t to be identically the 0 function. That is something that I don't want. Otherwise, our solution to the differential equation will just be the 0 function, and that'll satisfy just about everything except for that initial condition that we haven't touched on yet. So if I want this to be true, it's easier for me, or better for me, to just allow x of 0 to be equal to 0. And if I look at my second boundary condition, well, this is going to be x of L times t of t equals 0. Again, I don't want t of t to be equal to 0. That's saying that the t function is going to be 0 for every single value of t, every single point in time. Whereas letting x of L equal 0 says x is going to be 0 just at the right endpoint, and x of 0 equals 0 is saying x is going to be 0 at just the right endpoint. So here we have our two boundary conditions, okay? So let's go ahead and let's group these back together with our differential equation in x. So we'll have the differential equation x double prime minus lambda x equals 0, but we'll also have the boundary conditions x of 0 equals 0 and x of L equals 0. Right? So we have a second order linear homogeneous differential equation with constant coefficients. Okay. Here's the thing though. If we said, let's write down the solution of this differential equation, we might start with our characteristic equation, which in this case is going to look something like an m squared minus lambda equals 0. No big deal yet. And if we try to solve for m, we would end up with m equals plus or minus the square root of lambda. Again, really no big deal yet, except we don't know anything at all about lambda, okay? So what we really have to do is we have to consider three cases, because depending on what lambda is, we're going to end up with different solutions to the differential equation. So we're going to have to consider three cases. And those three cases are going to be what happens if lambda is greater than 0, what happens if lambda is equal to 0, and what happens if lambda is less than 0, because each of those are going to produce different results, right? So let's go ahead and let's look at these case by case. So case 1, let's say in this case we want to look at what happens if lambda is greater than 0, right? So in this case, the solution to our characteristic equation will be m equals plus or minus the square root of lambda. Well, here the square root of lambda is a real value term. So this is the case where our characteristic equation will have two real distinct roots. So what does that tell us about our function x? Well, this tells us that our function x is going to look something like a c1 times e to the root lambda x plus c2 times e to the negative root lambda times x. Great. Let's go ahead and let's apply our boundary condition then. So our first boundary condition is x of 0 equals 0. And if we plug 0 in for x, we get c1 plus c2. Fine. We can go ahead and we can solve for one of these in terms of the other. I like to solve for c2 in terms of c1. So here we can say c2 equals negative c1. I think that's reasonable. That's a reasonable statement to make. So let's go ahead and let's plug that back into our solution. So here we'll have x of x equals some c1 times e to the square root of lambda times x minus e to the negative square root of lambda times x. Right? And now we'll plug in our left endpoint. Sorry, we'll plug in our right endpoint, L. We use the letter L. I keep wanting to say left, but it's our right endpoint. So now we'll have a c1 times e to the square root of lambda times L minus e to the negative square root of lambda times L. Right? And we want this to be equal to 0. I should have mentioned that beforehand. So here's the thing, all right? This right here will never be equal to 0 because the exponents are different as long as L is positive. And remember, we're talking L is the length of the rod, so L can't be 0, and lambda can't be 0 either because we're in case 1 where lambda is strictly greater than 0. So what's in parentheses will never be equal to 0. So the only way for this to be true is if c1 equals 0. But if c1 equals 0, c2 was equal to negative c1 is also equal to 0. So that means that the solution to the differential equation in x is just the 0 function, which in and of itself isn't a problem. But remember, this is going to imply that u, the solution to the heat equation, which is a function of x times a function of t, but since x of x is equal to 0, the solution is just going to be 0. And here there's no way for this to satisfy that initial heat distribution throughout the length of the rod. There's no way that I can plug in 0 for t and leave x alone and get 2 out, okay? So we would call this a trivial solution. And to us, that implies that lambda cannot be greater than 0. So lambda either has to be 0 or it has to be negative. Right? So let's go ahead and let's look at case 2. This is a case where lambda is equal to 0. So the differential equation here basically just reads x double prime equals 0. And if you think about integrating 0 twice, you end up with something like x of x equals some c1 times x plus c2. You integrate 0 once, you get a constant. Integrate 0 again, you get that constant times x plus a different constant. Right? So again, we'll go ahead, we'll apply our boundary conditions. So x of 0 equals 0. If we plug in 0, we get c2 equals 0. So plugging that back in to our solution, here we're left with x of x equals c1 times L. Sorry, c1 times x. We'll plug in our second boundary condition. which is x of L, equals 0. Well, this time we'll have C1 times L, but L is the length of our rod. We can't talk about a rod of 0 length, so L can't be 0. So the only way for this to be true is if C1 is equal to 0. But if C1 equals 0, that means that x of x equals 0. But if x of x is 0, that implies that u of x and t is also equal to 0, which is a trivial solution. So what that tells me is that lambda cannot be equal to 0. All right, so we're kind of running out of choices of lambda. So hopefully lambda can be negative. Otherwise, all this thought process is going to be for naught. So let's go ahead and let's look at case 3. So what happens if lambda is less than 0? Okay, well, this is kind of interesting because here we end up with the solution to our heat equation, the solution to our characteristic equation is going to satisfy m squared minus lambda equals 0. So we're going to end up with m equals plus or minus the square root of lambda. But remember, lambda is less than 0. So now we're taking the square root of a negative quantity. So that's actually going to be a purely imaginary quantity. And we could write this as the square root of, let's make lambda positive. There's a couple ways to do it. You can either slap lambda in absolute values or take the negative of lambda. I'm going to put it in absolute values. Either way, get you the same answer in the end. Okay? All right, so here we can go ahead and we can finally write down what x of x is going to be equal to in this third case. It's going to be in terms of sines and cosines. So let's write it as some c1 times cosine of the square root of the absolute value of lambda times x plus some c2 times sine of the square root of the absolute value of lambda times x. We'll apply our first boundary condition, which says x of 0 equals 0. Plugging in 0 for x, we'll be left with the cosine of 0, which is 1 times c1 plus c2 times sine of 0, but sine of 0 is 0. So what we're left with is c1 has to be 0. We'll plug that back in. We'll rewrite our solution, which in this case is just going to look like x of x equals some c2 times sine of the square root of the absolute value of lambda times x. All right, last condition that we have to satisfy. So we also have to satisfy our second boundary condition, which is x of L equals 0. If we plug in L, we get c2 times sine of the square root of the absolute value of lambda times L. Finally, we're at a point where we have a function that is also sometimes equal to 0, okay? So c2, if we can have c2 non-zero, that's what we want, right? Because if c2 was 0, c1 and c2 would both be 0, and x would be 0, we'd have another trivial case. So what we're looking for is we're looking for values of lambda that cause this whole thing to be equal to 0 when c2 is not equal to 0. So what we want is we want sine of the square root of the absolute value of lambda times L to be equal to 0. But we know that sine is equal to 0 whenever its angle is equal to a multiple of pi, right? So sine is equal to 0 when you plug in 0, when you plug in 1 pi, 2 pi, 3 pi, 4 pi, and negative 1 pi, negative 2 pi, negative 3 pi, negative 4 pi, so on and so forth, okay? But just something to kind of keep track of here. Pi is always going to be a positive quantity. L is the length of the rod, is always positive. Absolute value of lambda is always positive. Take the square root of something positive, you're going to get something that's always positive out. So what we're really looking for here is we're looking for values of n that are positive, right? Because the square root of the absolute value of lambda times L is never going to be a negative quantity. All right, so let's go ahead and let's start thinking about how we would solve for lambda. So we can go ahead and we can divide both sides by L. Hey, this is going to be very convenient for us because we're going to be able to plug this back in right here in just a moment. So keep in mind that your square root of the absolute value of lambda is just going to be an n pi over L. And also, now we can square both sides, so we end up with the absolute value of lambda is going to be an n squared pi squared over L squared. And now we end up with lambda has to be either plus or minus n squared pi squared over L squared. But keep in mind, lambda in this case had to be less than 0. So we actually have to take the negative values of lambda. We can't take the positive values of lambda. So what we end up with is lambda has to be this negative n squared pi squared over L squared. And something to make a little note of here is now lambda actually depends on n. So lambda is a function of n. So we have these lambda sub n's, and because lambda depends on n, that means that our function x of x will also depend on n. So we'll have a constant times sine of, well, the square root of the absolute value of lambda, which we just said was n pi over L times x. But because we have different solutions for each value of n, that means that this constant out front also has to be a function of n. So now what the solution to our x differential equation looks like is it's going to look like this guy right here. Okay, so to keep building on this idea, right? We really can't do much more with our x differential equation, but we can jump back to our t differential equation. So it's been a minute since we've talked about t, so let's recall what t is. T had this differential equation, t prime minus lambda t equals 0. But we just did a whole bunch of math, and we found the only values of lambda that make sense. And those were those values of lambda that we found up here, those negative n squared pi squareds over L squareds. But because lambda depended on n, now t is also going to depend on n, right? So here, you can go ahead and you can substitute that value of lambda back in, and what you're going to end up with is a t squared plus an n squared pi squared over L squared times t equals 0. This is a first order linear differential equation with constant coefficients. And here you can actually solve this by using the same technique that a lot of us use to solve second order differential equations. We can just write down the characteristic equation, which in this case is going to be m plus n squared pi squared over L squared equals 0. You end up with roots to your characteristic equation, well, a root to your characteristic equation of m equals negative n squared pi squared over L squared. So you end up with a solution to your t differential equation, which is going to be some constant. We already used c's, let's use d. And that's going to be d times e to the negative n squared pi squared over L squared times t. But because your solution depends on n, let's call that a t sub n. And because for each value of n, you might have a different constant, let's call those d sub n's. All right. Solving that t differential equation, much easier. Okay. So now we can go ahead and we can actually write down the solution, or part of the solution, which remember, we said that u of xt was going to be our function of x times our function of t. Well, our x's look something like c sub n times sine of n pi over L times x, and our t of t's looks something like d sub n times e to the negative n squared pi squared over L squared times t. But now because each of these depended on n, what we really have is we have our product of our x sub n's and our t sub n's, and what that gives us is that gives us a different u sub n for each value of n. One little trick that we can pull here is what I see is that we have two constants that depend on n, c sub n's and d sub n's. We can combine those into a single, let's call it b sub n, times sine of an n pi over L times x times an e to the negative n squared pi squared over L squared times t. So what we have now is for any positive integer that you give me, any value of n that you give me, I can give you a different solution to the heat equation. Well, if I want the most general form of this, the general solution to the heat equation is going to look something like u of xt is going to be the sum of all of those other solutions. So we can write this as a sum from n equals 1 to infinity of these b sub n's times sine of n pi over L times x times e to the negative n squared pi squared over L squared times t. Okay, so here we have the general form of the solution to our heat equation. Now, there's one other condition that we have to apply, right? So the last thing we have to apply is our initial condition. So we said our initial condition read u of x 0 is f of x. And if we're trying to apply this initial condition, we're replacing our t with 0. So what we'll have is we'll have a b sub n times sine of n pi over L times x times e to the 0, which is just 1. But since we've already talked about Fourier sine series, we should recognize that this is just going to be nothing other than a Fourier sine series. And because we have our function f of x expressed as a Fourier sine series, we actually know what these b sub n's are going to be. Excuse me. So we can actually write down these b sub n's as 2 over L times the integral from 0 to L of our function f of x times sine of n pi over L times x and dx. So here, for any initial heat distribution, we actually have the solution to the heat equation. Let's see if we can actually go ahead and let's look at the example function that I gave you earlier. So I gave you a pretty simple one. I said for f of x equals 2, our b sub n's are going to be equal to 2 over L times the integral from 0 to L of our function 2 times sine of n pi over L times x dx. Fair enough. So let's go ahead and let's think about how we'd integrate this. I see a 2 times a 2, that gives me a 4. We'll have a 4 over L. And then if I integrate sine, that's going to leave me with a cosine of n pi over L times x. We're going to multiply by L, and we're going to divide by n pi. And then we're going to evaluate that from 0 to L. Right? So 4 over L is going to come along for the ride. And if we plug in L, we're going to have an L times cosine of n pi. Sorry, I made a mistake. When we integrate sine, we get a negative cosine. So let's bring that negative sign just out front. And that's going to be over n pi. And then from here, we're going to subtract off what we get when we plug in 0. Well, that's going to be a minus L over n pi. Right. So a few things that I'm seeing right away. I see that there are factors of L in all the numerators and the L out front. So we can actually cancel or reduce all of these L's. And then I also see that we have common denominators, so we can go ahead and we can combine our two fractions in the middle. So we'll have something that looks like a negative 4 times cosine of n pi minus a negative 4, so we can write that as a plus 4, all over n pi. So there are our b sub n's. So finally, we can tie this all back together, and what we have is we have u of xt is going to look like the sum from n equals 1 to infinity of our b sub n's were this negative 4 cosine of n pi plus 4 all over n pi times sine of n pi over L times x times e to the negative n squared pi squared over L squared times t. And that right there is the solution to our heat equation, subjected to the initial heat distribution of 2 degrees throughout the length of the rod. So let's go ahead and let's actually take a look at this in something like Desmos. So I might have to bounce back and forth here a little bit in order to get that copied down, but let's actually see what we did. All right. So we said the solution to our heat equation was going to look something like U equals, I'm going to use Y because I want U to be my vertical axis. And we said it looks something like the sum from n equals 1 to infinity. Desmos doesn't like it if I try to plug in an infinity, so I'm going to go ahead and I'm going to use k as my upper limit of summation. I'll go ahead and add a slider in there for k. And now what we have is we have to go ahead and enter our b sub n's, which, let me remind myself, negative 4 cosine of n pi plus 4 over n pi. So we'll have a negative 4 cosine plus a 4, I think it's just plus 4, right? Plus 4 divided by n pi. And that's going to be multiplied by sine of n pi over L times x times e to the power of a negative n squared pi squared over L squared times t. Right. So now what I'll do is I'll go ahead and I'll add in sliders for all of these. I'll go ahead and change some of the bounds. So I'll let k go from 0 to something like 50 with a step size of 1. I'll let L go from 0 to 10. Really, we're just going to fix that. And I'm going to let t go from 0 to, let's say, something like 5. Now, what I want to do is I want to slow down t a little bit because t is going to be what's changing. Let's go ahead and let's make L somewhat large. And we'll leave k right where it's at. Okay, so here's what we need to do. We knew that we had this initial heat distribution along the length of the rod as 2 degrees. And we really only want to look at that heat distribution on the interval from 0 to L. Okay. So this right here is our initial heat distribution. Let me go ahead and change the color. I'll change it to blue. And we really only also want to look at the solution to the heat equation on that interval from 0 to L as well. So let me also go ahead and include that domain restriction. Okay, so what we have is we have our initial heat distribution here in blue, and we have just the first term in our Fourier sine series down below. So watch what happens as I go ahead and I start adding more terms to my Fourier sine series. In other words, I'm increasing my upper limit of summation. That is much too fast for my liking. Sorry, folks. Sorry, folks. I did that a few times. I didn't notice that I noticed that t was not at 0. So now let's go ahead and let me do that again. So let's go ahead and press K, and we'll start increasing K. So what we see is that each time this ticks, we're adding another term to our Fourier sine series. So now we have this jumping up, and what we're looking like is we're finally building our initial heat distribution in terms of all of these sine functions. So let me actually go ahead and I'll slide that all the way up to 50. So what we have now is we have our initial heat distribution in terms of only the sine functions, and notice the endpoints of a rod are still held at 0 degrees. So now when I press play, what we're going to expect to happen will probably happen, right? We're going to imagine those ends are going to come down to 0 degrees right away, and then temperature is going to slowly fall as time progresses. So let's go ahead and press play on T. So what we see is that we are decreasing the temperature throughout the length of the rod down to 0 degrees, and the rate at which the temperature decreases is proportional to the concavity. So that right there is our first solution to our first heat equation problem. And really at this point, there's a couple different variants that we could look at. We could say, what happens if we change that initial heat distribution? Well, the thought process remains almost identical, except when we get to the very end, we have to change what our Fourier coefficients are going to be. The other changes that we could make is we could start thinking about how we would change our boundary conditions. So we could imagine, instead of holding the ends at 0 degrees, hold the ends at something other than 0 degrees, or hold them at 2 different temperatures, or perhaps put the ends in like isolated environments where the temperature at the end of the rod is equal to the temperature just a little past the ends of the rod. And each of those are going to present new and interesting variations of the same heat equation. So with that, I think I'm going to go ahead and leave the video here. If you do have any questions, please feel free to leave them in the comments below. Thank you for watching, and I will see you guys in the next one.